Sir Olenjolai Moko. I would like to welcome you into this fantastic YouTube channel. And the YouTube channel name is called Tanzania Online A-Level Secondary Schools. In the square bracket we have Olenjolai and we have M in the square bracket. We are in Department of Advanced Chemistry, and the subject that we are going to teach you today is called Advanced Chemistry. The main topic is General Chemistry, and also the topic is the atomic structure. And in case that you want to join us in the sense giving, please close that window. Okay, in the sense giving, then please you can send your sense givings on this telephone number. And this is lecture or session or period 13 as just a continuation of period 12. Okay, so I would like just to ask you that this is the serious program. Make sure that you take all the required tools for you to learn, because this is the real class. So I would like to ask you that to take your scientific calculator, take your exercise book, take your pen, have the earphones or have the loudspeaker so you can hear everything that I'm going to speak, and take your book, your textbook or your question and answers books, so that we may join together. The concept that I'm teaching you in this lecture is called the quantum number. And in lecture 12, I left this homework that describe briefly the meanings of magnetic quantum number. And the second question, describe briefly the meanings of 40 of the spinning quantum number. I believe that you have done that work effectively. So I would like to do minor correction for you. And I think that you have done. I encouraged you yesterday to make sure that you do this homework for the benefit of 40, for the benefits of your understanding. So let us continue with today's sessions. I'll do corrections on these two questions, and I would like to start with the 30 principal quantum number, because we say that we have four types of quantum number. We have principal quantum number, subscale quantum number, magnetic quantum number, and spine quantum number. So I would like to teach you in this lecture all about the 30 quantum number, which we call the magnetic. So this we call it in chemistry magnetic quantum number. So that's the name of this quantum number. So magnetic quantum number. So by notations we call it, or we have a notations of M subscript of 40 of S. So magnetic quantum number. And the fundamental question that when we'll be asked that to describe it briefly, the fundamental question is, we want to know its meaning. What is magnetic quantum number? Okay? What is magnetic quantum number in atomic structure? Magnetic quantum number. Okay? So we say magnetic quantum number. Okay? Magnetic quantum number is the quantum number. Okay, so this is the quantum number which determines the orientation, which determines the main functions of this quantum number, which determines the orientation, of the designated of electrons in the designated, or of the designated orbital, of the designated orbital. Designated orbital. So he said that magnetic quantum number is a quantum number which determines the orientation of the designated orbital. So that's the definition of 40 of magnetic quantum number. So it's the quantum number which determines orientations of the designated orbital. But basically, the main functions of this principal quantum of this quantum number is helping the physicists and the chemists to know the number of orbitals or no, yes, we call number of orbitals in the certain sub-energy level. Remember that I told you about subsidiary quantum number, which we say, I told you that it is a subsidiary energy level. It's just like a one, or it's a part of the principal quantum number. So this magnetic quantum number now is telling us how many orbitals are there, because in subsidiary quantum number, we have learned that we have four types of orbitals. We have the s orbital, the p orbital, the d orbital, and also the f orbital. In long terms, we call them sharp orbital. Then we have a principal orbital, we have also diffuse orbital, and finally we have fundamental orbital. So I told you, we learned about different shapes, the shapes of those orbitals, especially for the first 3 orbitals, but we didn't discuss about the number of orbitals. For example, that in s orbitals, how many orbitals are there where we can place electrons. So in this part, or in this principle, in this quantum number, we'll know the number of orbitals in s orbital. We'll know the number of orbitals in p orbital. We'll know how many orbitals are there in f orbital, or how many orbitals are there in the d orbital. In the subsidiary, we learn the shapes. We learn that according to the subsidiary quantum number, so we can know that the number of orbitals, and even sometimes that we can find because of the difference in the principal quantum number, we can have the same orbital, but at the different principal quantum number. So that's why it said that the principal quantum number usually acts as what a coefficient of the orbital name. So that's why we say that it is in this magnetic quantum number determines the orientations of designated orbitals. Okay. So again, we say that what the main function of this orbital, okay, or what does it do? So we say that magnetic quantum number which is first of is used to differentiate orbital. It's used to differentiate orbital that have the same shape, that have the same shape, have the same shape, okay, the same shape and what? Same shape and energy. The same shape and energy. But what? But differently, to say that they have different direction when they are subjected different direction. So they differ in different direction when they are subjected. So they have different direction when they are subjected to the magnetic field. So when they are subjected to the magnetic field, and this we call the Zeeman effect. Zeeman effect. Say Zeeman effect. So do your private study to know what it means of the Zeeman effect. Okay. So you say that magnetic quantum number in atomic structure is used to differentiate, right? What? Orbitals in plural. So we have S here, orbitals that have the same shape. Number one, they have the same shape, and also they have the same energy, but different directions when they are subjected to the magnetic field. When we say magnetic field, we know that if we need a magnetic field, we may use either a permanent magnet or we may use paramagnetic materials, especially some of the elements. So it means that they have different directions. So different directions, okay, I will tell you. So what means of different directions? For example, you might find that maybe because you have the subsidiary quantum number is equal to 1. So if we want now to, maybe we have a certain orbital that have the same energy level, the same energy and the same shape, but now different what I want to check about the direction. So the direction, we say that, for example, this one, its magnetic quantum number will be -1, and also its magnetic quantum number will be +1. So you see, so here we have -1, here we have +1. So we have two different directions. So that's the main functions of 40 of magnetic quantum number. However, that I'll be teaching you and build the foundations and step to step until that you understand. Even somebody will ask you to, or ask you some questions during the midnight when you are in the middle of the sleep, you can answer them. Okay, so that the main functions of this magnetic quantum number. So we say that the magnetic quantum number, so the magnetic quantum number is denoted as what? As m subscript lowercase m, or no, it's just lowercase m, yes, m, just m, or in some of the book we use m and then subscript of 1. So it might be m like this, or it might be what? M like this one, right? So you have this M or either this one. That is the notation for magnetic, so here we don't have a subscript of S. And even this one is not a subscript of S. So here we have lowercase m or m subscript of 1. That is the universal notations of 40 magnetic quantum number. So we say another sentence that I would like to make. We say that the total quantum number, the total magnetic quantum number, total magnetic quantum number is equal to the total number of orbitals, of that type. Total number of orbitals of that type. Number of orbitals of that type. So we'll use a simple example to explain what does it mean. Again, we say that the notation for the principal quantum number in lecture 11, the notation for the principal quantum number is n, and it's taking the possible number. And then I taught you in lecture 12 the notations or the symbol for subsidiary quantum number is L, and I told you the relationship between n and L. So remember that we say that n, or we say that L, this will be maybe starting from 0 and then still n at n minus 1. So this is the relationship between the subsidiary quantum number, which is the sub-energy level, and the principal quantum number, which is n minus 1. So that's the formula. So then we say that the general formula of magnetic quantum number, is given as this. So this is the formula. So you say that it is twice L plus 1. So what does it mean? It means magnetic quantum number m we can find by using twice times what? twice or 2 times subsidiary quantum number, which is L plus 1. So this is the general formula. We call it the n step. For example, if you are learning about sequence and series. So that's the n step, that's the general formula. So I will remember that I didn't explain clearly what the meaning of this sentence. That the total magnetic quantum number is equal to the total number of orbitals of that type. I will explain to you simply right now by using the example. Okay, so this is the general formula. So if that's the general formula, now we can learn something about the number of orbitals or number of orbitals in each sub-energy level. So I would like to teach you about the number of orbitals, determinations of numbers. So determination, so let us determine determination of number of orbitals, determination of number of orbitals in each sub-energy level. So in order to understand this part, because through this part you'll understand, I'll come to this point, so don't worry about that, because I gave you a promise. So it said that we have principal quantum number, which is L, and also we have subsidiary quantum number, which is, we have principal quantum number, which is noted as N. We have subsidiary quantum number, which is not denoted as what as L. And this starts from 0 to n minus 1. And then now, I told you about magnetic quantum number, which is general formula is twice L plus what? Plus 1. So let us see the relationship between the three, we say that between the three quantum numbers. So we have n here, we have L, possibly we have m there. Okay. So we say that suppose that n is equal to 1. So what will be the value of L? L will be 1 minus 1, which is equal to 0. And then for in case of magnetic quantum number, also its value at this point, we say that because m is equal to twice L plus 1. Then we say m is equal to twice times 0 plus 1. So magnetic quantum number for this case will be 2 times 0, which is 0, plus 1 is equal to 1. Okay, so what does it mean? We mean that when n is equal to 1 and L is equal to 0, this we say that representing what? S orbital, if you do remember that in lecture 12, S orbital. And also we say that in this S orbital we have only one we have only one orbital, because the spinning or the magnetic quantum number, it has a value of 40, it has a value of 1. So implying that there's one S orbital. So here we have only one S orbital. S orbital. Again, suppose that the principal quantum number is equal to 2. What do you say? So you say L is equal to what? 2 minus 2, and then 2 minus 1. This means that L is equal to 0, and all of S or L is equal to 1. So for magnetic quantum number, M is equal to what? To 0. So it will be twice times 0 plus 1. So here you have what? So 0 plus 1 is equal to what? Is equal to 1. Hence you have M against when L is equal to 2. L is equal to 1. So L is equal to 1 plus 1. So this is equal to what? 3. Okay? So you have is equal to 3. So because it's equal to 3, we say that the total number there, we have not 3, yes, 3, because 2 times 1 plus what? Plus 1 is equal to 3. So it means that when we consider, listen, because we say that when L is equal to 0, we have only one S orbital. You have only one s orbital. So here you have one s orbital, but this L is equal to 1. It's another orbital. If you do remember that I told you that in lecture 12, this is S and this is D. So according to the D, we have M is equal to 3. What does it mean? We say that when L is equal to 1, M is equal to 3, magnetic quantum number is equal to 3, and this means that there are three orbitals. That's why we have magnetic quantum number is equal to 3. So that's why we say that the goodness of the magnetic quantum number, it shows the number of orbitals. That's what I told you at the beginning. It shows us the number of orbitals contained in one sub-energy level. So this is S sub-energy level, or we say that, okay, this is NH level, this is sub-energy level, so we have only one orbital in S sub-energy level. In case of D, we have also how many orbitals? 3 orbitals, right? That's what we used to call the PX, PY, and POT, PZ, if you do remember in lecture 12. Don't get confused with this material, because you have to be careful, otherwise you can confuse them. And that's not my intention to confuse you, but to help you and to encourage you to love this stuff and make them your closest friend. Again, if the principal quantum number is equal to 3, then the subsidiary quantum number, the first one will be 3 minus 3, which is 0. Second one, 1, 3 minus 2. Third one is equal to what? We say that is 3 minus 1, which is 2. So in case of magnetic quantum number, for this case, we have different magnetic quantum number. The first one, when L is equal to 1, magnetic quantum number is equal to, when L is equal to 0, magnetic quantum number will be equal to 1. When L is equal, so this is when L is equal to 0. When L is equal to 1, magnetic quantum number is equal to what? 1 times 2, which is 2, plus 1 is 3. Then when L is equal to 2, now we say that this magnetic quantum number is equal to 5. So because we have discussed that this is S orbital, it has only one S orbital, and here we have only 3 P orbital. And then for this case, when M is equal to 5, it means that there are 5 orbitals. And if you do remember that this is S sub-energy level, and then this is what? So S, this is P sub-energy level, this is D. So the D sub-energy level has 5 orbitals. So it means that there are 5 orbitals, 5 orbitals in D sub-energy level. Here there are 3 orbitals in what? In P sub-energy level. Again, if the principal quantum number is equal to 4, the subsidiary quantum number, L, is equal to 0, then 1, then 2, then 3. So magnetic quantum number for the first value, when L is equal to 0, will be equal to 1. Again, so when L is equal to, so this L is equal to 0, so when L is equal to 1, is equal to 3. When L is equal to 2, then magnetic quantum number is equal to 5. We have discussed all those 3 sub-energy levels. When L is equal to 3 now, M is equal to 3 times 2, 6 plus 1 is 7. So what does it mean? We say that for this case, there are 7 orbitals. Orbitals in what? In F orbital, or in F sub-energy level. What the means of orbitals? Orbitals is a place where we expect or there's the highest probability to find what? Electrons. So when we feel electrons in the air shells, we don't feel them just generally like the way we taught you in O level. We feel electrons into the particular orbitals. And that's why that we are expanding your knowledge of atomic structure from the fundamental concept that you have. So then, if you have N is equal to 5, when you have the fifth sub-energy level, this is your homework. How many orbitals, or what are you going to generate first of all? How many sub-energy levels? Because here we have 1, 2, 3, 4 sub-energy levels, which you call them S. So this, remember that this is S orbital, this is P orbital, this is D orbital, this is F orbital. So according to the syllabus, we have to teach you only those 4 orbitals. Okay, so that is how we use the magnetic quantum number to know the number of orbitals in a particular sub-energy level, right? So again, another thing that we say that in the number of orbitals in sub-energy level, in S sub-energy level, is 1. So now the summary, can have the summary now of what we have been discussing, and this is number 1. So say that the number, very important contribution, the number of orbitals in S sub-energy. So from now, we call S sub-energy, not S orbital. In S sub-energy level is what? 1. So you have only one orbital. Number 2, the number of orbitals where we can fill electrons in what? In D sub-energy level. D sub-energy level is 3. So you have 3 orbitals. So remember that one orbital can accommodate only 2 electrons, right? So it means that in S sub-energy level we can fill only 2 electrons, not more than 1. The maximum number of electrons in S suborbital is only 2. The sub-energy level, it might not contain electrons. For example, ionize the ion, for example, hydrogen ions, when it is ionizing, then it is losing 1 electrons. So its S orbital will be empty. So we can have an empty, we can have empty orbital, we can have half-filled empty orbital, we can have full-filled orbital. This is very important because in the next lecture, I will teach you how to write the new electronic configuration. And the way that we are writing the electronic configurations depends on the number of electrons that within or we find in an element or in an atom. So you have to follow careful and you have to be serious in this stuff. Otherwise, I will leave you somewhere else. Okay. So the number of orbitals in this sub-energy level is equal to 3, according to that summary. And what the meanings of this sentence is what we found there. Then number 3, we say that the number of orbitals in what? This is p orbital. This is p orbital. The number of orbitals in this sub-energy level is 5. And you have determined, I showed you how do we get 5. Chemistry is beautiful, atomic structure is beautiful, general chemistry for advanced students is beautiful, so stay tuned. So you say that is 5. Then number 4, the number of orbitals in F sub-energy level. So this, we used to call this as orbitals because we are in the high level. Right now we are going for the low level, so we call this F sub-energy level is what? What did we find there? 7. Right? That's very important. Okay. So that is generally when we discuss about orbital. Right? So we say that an orbital is represented by what? Represented by a square. A square. So for example, when you say that we have one s orbital, it means that this is its representation. Right? So when you say that one s orbital can accommodate only 2 electrons. It might be this, or it might be that maybe one s orbital, maybe the atoms, for example the heliums or some other elements that maybe, or for example for magnesium, when it didn't ionize, then it has 2 electrons at the outside of at the valence shell. So also the orbital may be half filled, and also an orbital it might be empty filled, especially for ionized element. So these are the three states of orbital. So this is one S40 orbital. So this means that this we call the full filled orbital, and this one we call it the half filled. Half filled. I will teach you what the means of this sign. Half filled orbital. And this we call the empty orbital. This is a detailed study of empty orbital. Detailed study of atomic structure. Okay, so if that is all, now we can try to think again according to the principal quantum number of a particular shell of an atom, how many orbitals we might have. So we say that relationship between principal quantum number n and the number of orbitals. Number of orbitals. What does this sentence mean? The primary or the ground state, or the ground, we call the primary or the fundamental or the ground principal quantum number is n is equal to 1. Right? N is equal to 1. The subsidiary quantum number will be 0. Right? And then its magnetic quantum number will be 1. So, because it will be 1, we say that the principal quantum number n is equal to 1 contain, it has, so n is equal to 1 has only one s orbital. And this one s orbital, we have this notation 1s, because I told you that the coefficients of the subatomic level is the principal quantum number. So this is the first example, or the first relationship. The second relationship, we go for the second second principal quantum number, n is equal to 2. The subsidiary quantum number for this case, the first one will be 0, the second one will be 1. So when the first one will be 0, the magnetic quantum number for this case is 1, and also when L is equal to 1, the magnetic quantum number will be 2 times 1 plus 1, which is equal to 3. So this representing what? Be careful. M is equal to 1 representing contains only one orbital. M is equal to 1, this is an orbital, which is s orbital. But now we'll call it 2s orbital. M is equal to 3, this is what? It means that these are the 3 orbitals, and these are p orbital. Be careful. So for example, M is equal to 1, this is representing what? 2s orbital. M is equal to 3, this is representing 2p orbital. So it means that the principal quantum number n is equal to 2 has how many orbitals for that case? Has 1 s orbital, right? 1 s orbital, and 2s orbital, and then 2 and 3 what? And 3 has 1 2s orbital. So let me write in words. Has 1 2s orbital, and also has 3 has, and the 3 2p orbitals. So total number of orbitals that we find when n, total number of orbitals is equal to 4. 1 s orbital and 3 orbitals of p orbital, or of p sub n level. Again, we have to proceed when n is equal to 3. So there we have 3 subsidiary quantum number, L is equal to 0, and here M is equal to 1. So for this case, because the principal quantum number is equal to 3, we have 1s orbital. Again, L for this case will be equal to 1, whence magnetic quantum number is equal to 2, is equal to 3. So here we have